In 2006, NASA launched the fastest spacecraft ever to leave Earth. It crossed the orbit of the Moon in just 9 hours. It passed Mars in a few months. Then it kept going. For 9.5 years, it flew through the emptiest corridor in our solar system at over 36,000 miles per hour. When it finally reached Pluto, humanity celebrated. We had touched the edge of our cosmic neighborhood. But here is what nobody told you. If that same spacecraft turned toward the nearest star beyond our sun and never stopped, it would not arrive for another 78,000 years. The distance to Pluto nearly broke our patience. The distance to Proxima Centauri breaks something deeper. It breaks the way your brain understands far away. If you enjoy having your sense of scale completely dismantled, do me a favor and hit that like button and subscribe. It genuinely helps this channel keep making these deep dives, and I appreciate every single one of you who sticks around. Now, get yourself nice and comfortable. Let's begin. Picture the solar system as you learned it in school. The sun sits at the center, the rocky planets cluster close, the gas giants spread outward through the middle distance. And then, at the far edge of every classroom poster, sits a tiny dot labeled Pluto. That dot always looked like the last thing before nothing, the final outpost, the point where the solar system runs out of things to show you, and the map just ends. For most of human history, Pluto represented the boundary of everything we could imagine visiting. It was discovered in 1930 by a young astronomer named Clyde Tombaugh, working at the Lowell Observatory in Arizona. For 76 years after that, it remained a mystery, a faint smudge in even the most powerful telescopes, too far away to photograph clearly, too distant for any spacecraft to justify the trip. We knew almost nothing about what it looked like, what its surface was made of, or whether it had any geological activity at all. We had better images of galaxies millions of light years away than we had of this object in our own solar system. And that single fact tells you something important about how far away Pluto really is. Pluto orbits the Sun at an average distance of approximately 39.5 astronomical units. 1 astronomical unit is the distance between Earth and the Sun, roughly 93 million miles or 150 million kilometers. So when we say Pluto is 39.5 astronomical units away, what we are really saying is that Pluto is 39.5 times farther from the Sun than we are. In miles, that average distance works out to about 3.7 billion. In kilometers, approximately 5.9 billion. These numbers are so large that they stop functioning as numbers in any meaningful human sense. 3.7 billion miles. Your brain registers the words, nods politely, and then discards the information because it has no frame of reference for a quantity that enormous. So let us build one. Slowly. If you got in a car right now and drove toward Pluto at highway speed, say 65 miles per hour, without ever stopping for gas, food, or sleep, you would arrive in approximately 6,500 years. That is longer than the entire span of recorded human civilization. You would need to drive from the era of the first Egyptian pyramids straight through to the present day, and then keep going for another 1,500 years before your odometer clicked past the 3.7 billion mile mark. If you replace the car with a commercial jet flying at 550 miles per hour, the trip would still take roughly 770 years. At that speed, you would have departed during the reign of the medieval Mongol Empire, and you would not arrive at Pluto until today. 7 centuries of continuous flight at the cruising speed of a passenger airliner, and you would only just now be pulling into your destination. But those comparisons still feel abstract, because the speeds involved are human speeds applied to inhuman distances. So let us approach it differently. Let us forget about travel and think about something simpler: counting. Suppose you decided to count from 1 to 3.7 billion, one number per second, without pausing. No breaks, no sleep. Just a steady rhythm, one number every tick of the clock. How long would it take? Roughly 117 years. Longer than any human has ever lived. You would begin counting as an infant, pass through childhood, adolescence, adulthood, middle age and old age, and you would die still counting, having never reached the end. Your grandchildren could take up the task where you left off, and they would die counting too. It would take the combined lifetimes of at least 2 people, end to end, with no interruptions, just to count the number of miles between the Sun and Pluto. And every single one of those counts represents a real physical mile of empty space that a spacecraft must actually cross. Or think about it in terms of something you can hold in your hand. A sheet of standard printer paper is approximately 4/1000ths of an inch thick. If you stack sheets of paper on top of each other, one for every mile between Earth and Pluto, your stack would climb roughly 230 miles into the sky. That would place the top of your paper pile at the altitude of the International Space Station, well above weather satellites, well above commercial aircraft, and well into the vacuum of low Earth orbit. A pile of paper, made from 1 sheet per mile, reaching outer space, and each individual sheet in that stack represents 1 full mile of interplanetary space. The distance to Pluto is not just large, it is large on a scale that makes ordinary objects absurd when you try to map the two together. Now consider what this means in terms of light. Light is the fastest thing in the universe. It travels at 186,000 miles per second. A beam of light leaving the Sun reaches Earth in about 8 minutes and 20 seconds. That same beam, continuing outward past Mercury, past Venus, past our planet, past Mars and the asteroid belt, past Jupiter and Saturn and Uranus and Neptune, finally reaches Pluto after approximately 5.5 hours. 5.5 hours just for light, not for a spacecraft, not for a radio signal carrying data. For light itself, the fastest phenomenon physics permits. When sunlight lands on the icy plains of Pluto, it is showing the dwarf planet a version of the Sun that existed 5.5 hours ago. Pluto lives in a permanent time delay from the rest of the solar system. It exists on the other side of a communication gap so wide that even the universe's speed limit needs half a working day to bridge it. There is another way to feel this distance that most people never consider. Pluto is so far from the Sun that sunlight, which feels so overwhelming on a summer afternoon here on Earth, arrives there as barely more than a bright glow. From Pluto's surface, the Sun would appear roughly 1/900th as bright as it does from Earth. Scientists describe this as roughly equivalent to the amount of light you experience during the final few minutes before sunset on a clear evening. That specific moment, when the world begins to dim, and shadows stretch long, and colours drain toward grey, that is noon on Pluto. High noon, as bright as it ever gets, and it looks like twilight on Earth. If you stood on Pluto's nitrogen ice plains and looked up, you would see the Sun, not as the blazing disk that dominates our sky, but as an intensely bright star. Recognizable, yes. Powerful enough to cast faint shadows, yes, but nothing like the furnace we experience from 93 million miles away. 3.7 billion miles of distance has taken the most powerful object in our solar system and reduced it to a bright point in a dark sky. That is what distance does. It does not merely separate objects. It diminishes them. This is the distance that NASA decided to cross when it approved the New Horizons mission. And the story of that mission tells you everything you need to know about how brutally far Pluto really is. New Horizons launched on January 19th, 2006, from Cape Canaveral, Florida. It rode an Atlas V rocket with an added solid rocket booster stage, and when that final stage finished firing and released the spacecraft into its cruise trajectory, New Horizons was traveling at approximately 36,000 miles per hour relative to Earth. That made it the fastest spacecraft ever launched from our planet at the time of its departure. To appreciate that speed, consider that a bullet fired from a high-powered rifle travels at roughly 1,700 miles per hour. New Horizons left Earth at more than 20 times that velocity. If you could somehow fire a bullet and then fire New Horizons alongside it, the spacecraft would pull ahead so quickly that the bullet would look like it was standing still. At that speed, New Horizons crossed the orbit of the Moon in just 9 hours. It took the Apollo astronauts 3 days to make that same trip. New Horizons did it before most Americans had finished their workday. It passed the orbit of Mars in a matter of months. It was screaming through the solar system faster than any human-made object had ever departed Earth. And it still was not going fast enough. The mission planners knew from the beginning that even 36,000 miles per hour would not get New Horizons to Pluto in a reasonable timeframe without help. So they aimed the spacecraft at Jupiter. On February 28, 2007, a little over a year after launch, New Horizons made its closest approach to the giant planet, passing within about 1.4 million miles of Jupiter's cloud tops. The encounter was not for sightseeing, although New Horizons did capture stunning images of Jupiter's atmosphere and moons during the flyby. The real purpose was gravity. Jupiter's immense mass, 318 times the mass of Earth, acted like a gravitational slingshot, bending the spacecraft's trajectory and accelerating it by an additional 9,000 miles per hour. After the Jupiter flyby, New Horizons was traveling at approximately 51,000 miles per hour relative to the Sun. That gravity assist shaved 3 full years off the trip to Pluto, and then came the long silence. After Jupiter, there was nothing. No more planets to visit, no more gravity assists to collect. Just the vast emptiness of the outer solar system stretching ahead for billions of miles. New Horizons entered a hibernation mode. Most of its instruments were powered down. Its onboard computer monitored basic systems and sent a weekly status signal back to Earth, a single electronic heartbeat confirming that the spacecraft was still alive and still flying. Mission controllers woke it up briefly each year to calibrate its instruments and run system checks. Then they put it back to sleep. This hibernation lasted for most of the journey. Think about that. The spacecraft was launched with enormous fanfare, executed a spectacular Jupiter flyby, and then effectively went silent for years. The mission team at the Johns Hopkins Applied Physics Laboratory went about their lives. They published papers, they attended conferences, they worked on other projects. Some of them changed jobs. Some of them retired. Children who were toddlers at launch entered middle school. The iPhone was introduced, became ubiquitous, and went through 8 generations of redesign. Twitter was founded, grew into a global platform, and changed its name. An entire technological era passed on Earth, while New Horizons drifted through the darkness at 50,000 miles per hour, covering roughly 300 million miles per year, and still not arriving at its destination. The void that New Horizons crossed during those years of hibernation deserves its own attention, because it is not the kind of emptiness that most people picture when they think about space. Between Jupiter and Pluto there is almost nothing. Occasional chunks of ice and rock, separated by millions of miles of vacuum. No stars nearby enough to provide navigational reference points against the background. No planets to photograph. No dust clouds to study. The spacecraft was flying through the closest thing the solar system offers to true nothingness. A corridor so barren that weeks and months passed without any scientific target worth pointing an instrument at. The mission team had planned for this, designed for this, but the human reality of it was stark. For years, the most distant active spacecraft in the solar system was hurtling through blackness, alone, with no human hand to guide it and nothing on the horizon. 9 years and 5 months after launch, on July 14th, 2015, New Horizons finally reached Pluto. It flew within approximately 7,800 miles of the surface, at a velocity of about 31,000 miles per hour. The spacecraft could not slow down. No propulsion system available to humanity could have carried enough fuel to decelerate a spacecraft moving at that speed in the deep outer solar system. New Horizons had to do everything at full sprint. It captured images. It measured atmospheric composition. It mapped surface features. It recorded data on Pluto's 5 known moons. All of this happened during a flyby window that lasted only a few hours, after a journey that had consumed nearly a decade. And here is what made the moment truly agonizing. When New Horizons was closest to Pluto, It could not talk to Earth and observe the dwarf planet at the same time. Its antenna had to point in one direction or the other. The mission team chose science. They aimed the instruments at Pluto and let the spacecraft go silent during the most important hours of the entire mission. For roughly 22 hours, no one on Earth knew whether the flyby had succeeded. New Horizons might have struck a piece of debris in the Pluto system. It might have malfunctioned. It might have failed in a dozen ways that no one would discover until the spacecraft turned its antenna back toward home. When it finally did transmit its status signal, that signal traveled at the speed of light, 186,000 miles per second, and it still took 4 hours and 25 minutes to reach Earth. 4.5 hours of waiting after the spacecraft had already confirmed it was safe. The signal crossed 3 billion miles of empty space at the maximum speed the universe allows, and the journey still consumed most of a morning. Mission controllers at the Applied Physics Laboratory erupted in celebration when the signal arrived. The flyby had worked. The data was intact. New Horizons had delivered humanity's first close-up look at Pluto, and what it revealed was astonishing. Pluto was not a dead, cratered ball of ice. It was geologically active. Vast plains of nitrogen ice, smooth and crater-free, suggested that the surface had been reshaped in the geologically recent past. Towering mountains of water ice, some reaching heights of 11,000 feet, lined the edges of a heart-shaped formation now named Tombau Regio. Glaciers of frozen nitrogen appeared to flow slowly across the surface. A thin atmosphere of nitrogen, methane, and carbon monoxide produced haze layers visible in backlit images. Pluto was alive in ways that no one had predicted. This tiny world, smaller than Earth's moon, sitting 3.7 billion miles from the Sun, in temperatures plunging to minus 387 degrees Fahrenheit, was doing things that demanded explanation. But the data took 16 months to arrive. New Horizons could transmit information back to Earth at roughly 1 to 2 kilobits per second at Pluto's distance. To put that in perspective, a basic dial-up internet connection from the 1990s operated at 56 kilobits per second. New Horizons was transmitting data from the edge of the solar system at a rate roughly 30 to 50 times slower than the most primitive internet your parents ever used. Each image, each spectrometer reading, each particle measurement had to be broken into tiny packets and beamed across billions of miles at a trickle. The full dataset did not finish downloading until late October of 2016, more than a year after the flyby. This is what it means to visit Pluto. A 9.5-year flight at speeds exceeding 30,000 miles per hour, a gravity assist from the largest planet in the solar system. Years of hibernation crossing a void so vast that nothing of any significance exists within it. A few hours of frantic data collection during a flyby that could not be slowed, stopped, or repeated. And then more than a year waiting for the results to dribble back across the solar system at a pace that would embarrass a fax machine. Pluto is not just far away. Pluto is far away in a manner that challenges the fundamental logistics of space exploration. It stretches mission timelines beyond the careers of the people who design them. It makes communication so slow that simple commands require round-trip waiting times approaching 9 hours. It demands a spacecraft that can survive a decade of solitary flight without maintenance, without repair, without any human intervention at all. And it sits in a region of the solar system so sparsely populated with sunlight that solar panels are useless. New Horizons carries a radioisotope thermoelectric generator, a device that converts heat from decaying plutonium into electricity, because at Pluto's distance, the Sun is too faint to power conventional systems, and Pluto is not even at the edge of anything. This is the part that begins to crack the illusion. Pluto orbits within the Kuiper Belt, a vast ring of icy bodies stretching from about 30 astronomical units from the Sun out to approximately 55 astronomical units. The Kuiper Belt contains hundreds of thousands of objects larger than 12 miles across, and potentially trillions of smaller ones. It is the source of most short-period comets that occasionally grace Earth's night sky. Pluto is the largest known object in this region, which is partly why Clyde Tombaugh found it first, but it is far from alone. Eris, Makemake, Haumea, and hundreds of other dwarf planets and icy bodies orbit in the same general zone. New Horizons, after passing Pluto, went on to fly by one of these objects, a small Kuiper belt body named Arakoth, on January 1st, 2019. At a distance of approximately 43 astronomical units from the Sun, the Kuiper belt is enormous, but it is still part of the solar system. It is still under the gravitational influence of the Sun. Objects within it still orbit our star, even if those orbits take hundreds of years to complete. Beyond the Kuiper belt lies a hypothetical structure called the Oort cloud, a vast spherical shell of icy debris that may extend outward to 100,000 astronomical units or more. If the Oort cloud exists as models predict, the Sun's gravitational influence stretches far beyond Pluto, far beyond the Kuiper belt, into a region so remote that objects there take millions of years to complete a single orbit. Pluto, in other words, is not the edge. It is not even close to the edge. It is a familiar landmark near the start of a much larger suburban sprawl that still belongs to our star. The Kuiper belt is the Sun's outer yard. The Oort cloud, if it exists, is the fence at the far boundary of the property, and beyond that fence lies the real distance. The gap between our Sun and the next nearest star, a gap so staggeringly enormous that everything you have just known about Pluto, every mile, every year, every agonizing hour of waiting for signals to cross 3 billion miles of space, shrinks to almost nothing. We flew to Pluto, and it took 9.5 years. We celebrated as if we had reached the edge of the possible, and in many ways we had. Pluto represents one of the most extreme achievements in the history of human exploration. No crewed spacecraft has ever traveled anywhere close to that distance. No robotic mission has ever returned data from a more remote, targeted flyby. The New Horizons team pushed technology, patience, and mission planning to their absolute limits to make that encounter happen. But Pluto is not the edge of the possible. It is the edge of the familiar. It is the last destination we can point to on a solar system map and say, "We have been there." Beyond it lies a distance so radically different in scale that comparing it to Pluto is like comparing a puddle to the Pacific Ocean. And the destination waiting on the far side of that distance is not some hypothetical object in deep space. It is the nearest star beyond our Sun. It has a name. It has planets. And it is so incomprehensibly far away that the journey to Pluto, the journey that consumed a decade of flight and 3 billion miles of empty space and 4.5 hours of light-speed signal travel, would not even register as a rounding error on the trip. That star is called Proxima Centauri, and what comes next will permanently change the way you think about distance. You now understand Pluto. You understand the 9.5 years of flight. You understand the 3.7 billion miles. You understand the 5.5 hours of light travel time, the 4.5 hour communication delay, and the 16 months it took just to download the pictures. Pluto has settled into your mind as something genuinely far away, something at the very edge of what human engineering can reach. That feeling is correct. Everything you felt about Pluto's distance is real. But what comes next is going to take that feeling and crush it. There is a star called Proxima Centauri. It is the nearest star to our Sun. Not the nearest bright star. Not the nearest interesting star. The nearest star, period. Out of the roughly 400 billion stars in the Milky Way galaxy, Proxima Centauri is the one that happens to be closest to us. If you were drawing a map of the Sun's immediate stellar neighbourhood, Proxima Centauri would be the first dot you placed after our own. It is our next-door neighbour, in the most literal cosmic sense available, and it is 4.24 light-years away. That number sounds small. 4.24. It fits comfortably in a sentence. It does not look intimidating on a page, compared with the vast scales of the galaxy, where stars can be tens of thousands of light-years apart. 4.24 light-years seems almost modest. almost reachable. Your brain hears it and files it alongside Pluto's distance as another entry in the category of things that are far away. But here is where your brain makes a catastrophic error. It assumes those two entries belong in the same category. They do not. To understand why, we need to convert that distance into a unit we have already been using. Pluto's distance is measured in astronomical units. 1 astronomical unit equals the distance from Earth to the Sun, approximately 93 million miles. Pluto orbits at an average of 39.5 astronomical units from the Sun. We spent the first stretch of this story establishing what that distance feels like. Now, let us ask a simple question. 10. How many astronomical units is 4.24 light years? 1 light year equals approximately 63,241 astronomical units. Multiply that by 4.24. The answer is roughly 268,000 astronomical units. Let that settle for a moment. Pluto is 39.5 astronomical units from the Sun. Proxima Centauri is approximately 268,000 astronomical units from the Sun. Divide the second number by the first. Proxima Centauri is roughly 6,800 times farther away than Pluto. Not 6 times farther, not 68 times farther, not even 680 times farther. 6,800 times farther. The nearest star to our solar system, the closest possible interstellar destination, the very first step beyond our Sun's neighborhood, is nearly 7,000 times more distant than the object that already took us 9.5 years to reach. Think about what that ratio means in concrete terms. If you compress the entire distance from the Sun to Pluto into a single inch on a ruler, the distance to Proxima Centauri would stretch to 567 feet. Pluto would sit 1 inch from the Sun. Proxima Centauri would be almost 2 football fields away. You would need binoculars to see the far end of that distance from where the Sun was sitting. And remember, that single inch already represents 3.7 billion miles of real space. That single inch already consumed nearly a decade of New Horizons operational life. That single inch already pushed human engineering to its limits. Now multiply it by 6,800. This is not a gradual increase. This is not a smooth ramp from one distance to a slightly larger one. This is a cliff. The gap between Pluto and Proxima Centauri is not an extension of the solar system distance. It is a completely different kind of distance altogether. It belongs to a different category, operates on a different scale, and obeys a different set of practical constraints. Everything we know about how to reach places in the solar system, every gravity assist, every orbital mechanic trick, every fuel budget and mission timeline, applies comfortably to the space between the Sun and Pluto. None of it transfers meaningfully to the void between the Sun and Proxima Centauri. Before we explore what that void means for travel, let us understand what Proxima Centauri actually is. It is not a star like our Sun. It is a red dwarf, the most common type of star in the Milky Way. Red dwarfs make up more than 70% of all stars in the galaxy, but they are so dim that not a single one is visible to the naked eye from Earth. Proxima Centauri has a mass of roughly 12.5% of the Sun's mass. Its diameter is about 1/7 of the Sun's diameter, making it only about 50% larger than the planet Jupiter. It burns at a surface temperature of approximately 3,100 Kelvin, compared with the Sun's 5,700 Kelvin. It is so faint that despite being the closest star to our solar system, it was not discovered until 1915, when the Scottish astronomer Robert Innes identified it at the Union Observatory in South Africa. You could stare at the night sky for an entire lifetime and never notice the star that happens to be closest to us. That is how dim it is. Proxima Centauri is part of a larger system. It belongs to the Alpha Centauri star system, a triple star arrangement located in the southern constellation of Centaurus. The two main components are Alpha Centauri A and Alpha Centauri B. Alpha Centauri A is a yellow star very similar to our Sun in size, mass, and temperature. Alpha Centauri B is slightly smaller and cooler, an orange star that orbits Alpha Centauri A in a roughly 80-year cycle. These two stars are bright enough to appear as a single brilliant point of light to the naked eye, making Alpha Centauri the third brightest star visible in Earth's sky. They sit approximately 4.35 light-years from Earth. Proxima Centauri orbits this pair at an enormous distance, roughly 13,000 astronomical units from Alpha Centauri A and B, taking about 550,000 years to complete a single orbit. It is so far from its companion stars that it earned its separate name, Proxima, from the Latin for nearest, because despite being gravitationally bound to Alpha Centauri A and B, it is slightly closer to us than either of them. The difference is small, only about 1/10 of a light year, but it is enough to make Proxima Centauri the official title holder, the nearest star to the Sun. Now, what makes Proxima Centauri more than just a distance marker is what orbits it. In 2016, a team of astronomers led by Guillaume Anglada Escudé announced the discovery of a planet orbiting within Proxima Centauri's habitable zone. This planet, designated Proxima Centauri b, has a minimum mass of approximately 1.07 times that of Earth, based on the most recent measurements. It orbits its star at a distance of only about 4.7 million miles, completing one orbit every 11.2 Earth days. Because Proxima Centauri is so much dimmer and cooler than our Sun, this close orbit places the planet within the zone where liquid water could theoretically exist on its surface. Proxima b is the nearest known exoplanet to Earth. It is, in a very real sense, the closest possible destination outside our solar system, where the conditions for life might exist. In 2022, astronomers announced a candidate for a third planet, Proxima Centauri d, with a mass only about 1/4 that of Earth, orbiting extremely close to the star with a period of just over 5 days. In 2025, the Near-Infrared Planet Searcher instrument, known as NIRPS, installed at the La Silla Observatory in Chile, independently confirmed the existence of both Proxima b and Proxima d. That same analysis cast serious doubt on the existence of a previously proposed second planet, Proxima c, finding the evidence inconclusive at best. So the current confirmed picture, as of the most recent peer-reviewed results, is 2 planets, Proxima b, a roughly Earth-mass world in the habitable zone, and Proxima d, a much lighter planet orbiting too close to the star to support liquid water. Meanwhile, in a separate and remarkable development, the James Webb Space Telescope detected strong evidence in 2024 and 2025 for a candidate gas giant planet orbiting Alpha Centauri A. This possible planet, roughly the mass of Saturn, appears to orbit within the habitable zone of the nearest Sun-like star to Earth. However, follow-up observations in February and April of 2025 did not redetect the object, likely because its orbit carried it too close to the star for the telescope to resolve. Researchers have predicted that if the planet is real, it should reappear in observations scheduled for August of 2026. If confirmed, it would be the closest known planet orbiting in the habitable zone of a Sun-like star. The Alpha Centauri system is not just a distance benchmark, it is an active frontier of planetary discovery. But none of this changes the brutal arithmetic of distance. Proxima Centauri and its planets exist 4.24 light-years from our Sun. To fully understand what that distance means, we need to unpack what a light-year actually is, not as a convenient astronomical unit, but as a measure of physical space that a real object would need to cross. Light travels at 186,000 miles per second, not per hour, per second. In the time it takes you to blink, light has traveled from New York to Los Angeles and back roughly 24 times. In 1 minute, light covers just under 11.2 million miles. In 1 hour, approximately 670 million miles. In 1 day, roughly 16 billion miles. And in 1 year, approximately 5.88 trillion miles. That is 1 light year. 5.88 trillion miles. Written out in full, That number is 5,880,000,000,000 miles. A single light year contains more miles than most people will encounter numbers in their entire lives. Now multiply that by 4.24. The distance to Proxima Centauri works out to approximately 24.9 trillion miles, nearly 25 trillion miles of empty space between our Sun and the nearest star. This space contains almost nothing. No planets, no asteroids, no gas clouds dense enough to detect with ordinary instruments. Just vacuum, stretched across a distance so vast that light itself, the fastest thing the universe permits, requires more than 4 years to cross it. When you look at Proxima Centauri through a telescope tonight, assuming you have a telescope powerful enough to see an 11th magnitude star, the light entering your eye left that star 4 years and 3 months ago. You are not seeing Proxima Centauri as it exists now. You are seeing it as it was before the most recent United States presidential election cycle began. Any event happening at Proxima Centauri right now, a massive flare, a planetary impact, or the rise or fall of a hypothetical civilization, will remain invisible to us for more than 4 years. And any message we sent in response would take another 4 years to arrive. The round-trip communication time between Earth and Proxima Centauri is approximately 8.5 years. Compare that to Pluto, where the round-trip communication delay is roughly 9 hours. The delay to Proxima Centauri is not 9 hours. It has been nearly a decade. Now, let us put the distance in terms we have already internalized. Earlier, we established that light from the Sun takes approximately 5.5 hours to reach Pluto. That light travel time gave Pluto a feeling of extreme remoteness. The Sun's light to Proxima Centauri takes 4 years and 3 months, not hours, years. Pluto lives 5.5 light hours from the Sun. Proxima Centauri lives 4 light years from the Sun. The ratio between those two light travel times is the same ratio we already calculated, roughly 6,800 to 1. Every way you measure it, the answer stays the same. Proxima Centauri is not merely farther than Pluto. It is farther than Pluto by a factor so large that the comparison stops functioning as a comparison and starts functioning as a category break. Let us try to make this tangible. Imagine you are standing on a long, straight road that stretches from your front door to the horizon and beyond. You take 1 step forward. That single step represents the entire distance from the Sun to Pluto. Every mile New Horizons flew, every year it spent in hibernation, every hour mission controllers waited for signals to crawl across 3 billion miles of space, all of it compressed into that 1 step. Now look down the road ahead of you. To reach Proxima Centauri, you would need to walk approximately 3.8 miles, 1 step for Pluto. 3.8 miles for Proxima Centauri. That is the ratio. You took 1 step and thought you had gone somewhere. You had not even left your street. Or consider it in terms of time, using an analogy that has nothing to do with speed or travel. If the distance to Pluto were represented by a single day, 24 hours from midnight to midnight, the distance to Proxima Centauri would be represented by more than 18.5 years. You would live through childhood, adolescence, and reach voting age in the time it took to count out the distance to the nearest star, scaled against a single day spent counting the distance to Pluto. That is how much larger the interstellar gap is. Not a little larger, not impressively larger, categorically, devastatingly, incomprehensibly larger. And here is the part that quietly demolishes everything you thought you understood about the structure of space. The void between the Sun and Proxima Centauri is not unusual. It is not an exceptionally large gap between stars. It is, in fact, one of the smallest stellar gaps in the entire galaxy. The average distance between stars in the Milky Way's disk is roughly 5 light years, and in many regions it is much larger. We happen to live in a relatively crowded neighborhood, cosmically speaking, and Proxima Centauri happens to be unusually close. This is the best case. The shortest interstellar trip the universe offers us from our current position. Every other star in the galaxy is farther away, most of them enormously farther. If the nearest star already sits 6,800 times beyond Pluto, the second nearest star lies even further beyond that, and the distances only grow from there. The next nearest star system after Alpha Centauri is Barnard's star, approximately 6 light-years away. After that, Wolf 359 at roughly 7.9 light-years, then Lalande 21185 at 8.3 light-years. Each successive neighbour adds trillions of miles to the journey. By the time you have listed the 10 closest stars to the Sun, you are already dealing with distances of more than 10 light-years, which translates to more than 630,000 astronomical units. More than 16,000 times the distance to Pluto. The nearby stellar neighbourhood is not a crowded place. It is a scattering of isolated points separated by abysses of empty space that dwarf everything inside our solar system. This emptiness is worth pausing on, because it is not the kind of emptiness most people imagine when they hear the word space. The space between planets in our solar system is empty in the sense that it contains no large solid objects, but it is still threaded with the solar wind, a stream of charged particles flowing outward from the Sun at hundreds of miles per second. It still contains trace amounts of dust. It still sits within the Sun's magnetic field, the heliosphere, which creates a measurable boundary between our star's influence and the interstellar medium. When Voyager 1 crossed that boundary in 2012 at a distance of approximately 122 astronomical units, it was a scientific milestone, precisely because it meant the spacecraft had left the Sun's protective bubble and entered the space between stars. But Voyager 1, at 122 astronomical units from the Sun, had covered less than 1/20th of 1% of the distance to Proxima Centauri. It had barely scratched the surface of interstellar space. The void beyond the heliosphere, the true interstellar medium, stretches for tens of thousands of astronomical units in every direction before you encounter another star's influence. This medium is thin, almost beyond description. The density of the local interstellar medium is roughly 1 atom per cubic centimetre. For comparison, the air you are breathing right now contains approximately 25 quintillion molecules per cubic centimetre. Interstellar space is not just empty. It is empty in a way that makes the vacuum between planets look practically crowded. This is the space that separates us from Proxima Centauri. 25 trillion miles of near-perfect vacuum, carrying only scattered hydrogen atoms, trace helium, wisps of cosmic dust, and the occasional cosmic ray streaking through at close to light speed. No landmarks, no waypoints, no gravitational assists from conveniently placed planets, no way to refuel, no way to repair, no way to communicate with home faster than the speed of light allows. The journey to Pluto was long, but it passed through the Sun's domain. It flew past planets. It used Jupiter's gravity. It had context. The journey to Proxima Centauri passes through nothing. Just void, uninterrupted and featureless, for a distance nearly 7,000 times greater than the one that already exhausted our patience and our engineering. And this is where the real shock begins to crystallize. Pluto felt like the edge of the possible. It took almost a decade to reach. It pushed every boundary of mission design, and in the context of the distance to Proxima Centauri, the entire journey to Pluto does not even qualify as a meaningful fraction of the trip. If the distance to Proxima Centauri were a marathon, 26.2 miles of running, the distance to Pluto would be approximately 20 feet. Not 20 miles, 20 feet. You would not have left the starting line. The gun would have fired, you would have taken a few strides, and every spectator along the course would still be staring at you, standing almost exactly where you began. This is the fundamental deception that the solar system plays on human intuition. Because Pluto is the farthest well-known destination we have ever visited, and because visiting it was genuinely difficult, our brains file it under extremely far away. We use Pluto as a benchmark for maximum distance. We say things like, all the way out to Pluto, as though reaching Pluto means you have crossed some meaningful fraction of the gulf between stars. You have not. Reaching Pluto means you have crossed approximately 1/6800th of the distance to the nearest star. It means you have walked to your mailbox and declared that you have begun your journey across the continent. The mailbox is real. The journey was real. The effort was real. But the continent does not care about your mailbox. Proxima Centauri sits at 4.24 light-years, 268,000 astronomical units, 25 trillion miles. It is the nearest star. It has confirmed planets. One of those planets orbits in the habitable zone. It is the single most obvious first destination for any civilization that dreams of reaching another star. And it is so far away that the most impressive voyage in the history of human space exploration, the New Horizons mission to Pluto, covers roughly 15,000ths of 1% of the distance. We celebrated reaching Pluto as if we had touched the edge of the solar system. In many ways, we had. But the edge of the solar system is not the edge of anything that matters for interstellar travel. It is the front step, and the walk from the front step to the nearest neighbouring house is so preposterously long that it redefines what walking means. The question now becomes obvious. If Pluto took 9.5 years, how long would it take to reach Proxima Centauri? And the answer, at every speed we test, is going to do something deeply uncomfortable to the way you think about what is possible. We have established two distances. Pluto sits roughly 3.7 billion miles from the Sun, at an average of 39.5 astronomical units. Proxima Centauri sits approximately 24.9 trillion miles away, at roughly 268,000 astronomical units. The ratio between them is approximately 6,800 to 1. Now we are going to do something that will make that ratio feel physically real. We are going to send a spacecraft to both destinations at the same speed and compare how long each journey takes. Then we are going to increase the speed and increase it again and again and again, each time pushing into velocities that are currently beyond human engineering, some of them far beyond. At every single speed tier, we will watch the Pluto journey shrink towards something manageable while the Proxima Centauri journey barely flinches. The category gap between these two destinations does not close with better technology. It compresses slightly, but it never disappears. That is the lesson these comparisons exist to teach. Let us start where we are, right now, with the fastest spacecraft humanity has ever pointed at the outer solar system. New Horizons left Earth in 2006 at approximately 36,000 miles per hour. After its Jupiter gravity assist, it reached roughly 51,000 miles per hour relative to the Sun. By the time it arrived at Pluto, it had slowed somewhat due to the Sun's gravitational pull, passing the dwarf planet at about 31,000 miles per hour. For simplicity, let us use a representative cruise velocity of approximately 36,000 miles per hour, which is a reasonable average for the outbound journey. At that speed, New Horizons reached Pluto in 9.5 years. You know this story, you lived through the waiting. You remember the launch, the silence, the hibernation, and the triumphant flyby images that took 16 months to download. 9.5 years felt long. It was long. The mission outlasted 2 presidential administrations and an entire generation of smartphone technology. Now, point that same spacecraft at Proxima Centauri. Same speed, same trajectory, same 36,000 miles per hour, sustained indefinitely through the interstellar void with no gravity assists and no deceleration. How long does the trip take? Approximately 78,000 years. Not 78 years, not 780 years, 78,000 years. If New Horizons had launched toward Proxima Centauri at the same time it actually launched toward Pluto in January of 2006, it would arrive at the nearest star around the year 80,000. The entire recorded history of human civilization spans roughly 5,000 years. New Horizons would need to fly for more than 15 times that span. Every empire that has ever risen and fallen, every language that has ever been spoken and forgotten, every war and peace and revolution and renaissance, stacked end to end 15 times over, and the spacecraft would still be in transit. The Egyptian pyramids were built approximately 4,500 years ago. New Horizons would pass through 17 full pyramid-to-present intervals before reaching Proxima Centauri. 9.5 years to Pluto, 78,000 years to Proxima Centauri. Both numbers are generated at the same speed. The only difference is the distance. And that difference is so enormous that it transforms a decade-long mission into a journey that would outlast every civilization Earth has ever produced. Now, let us consider the Voyager spacecraft. Voyager 1, launched in 1977, is currently the most distant human-made object in existence. It is travelling away from the Sun at approximately 38,000 miles per hour, slightly faster than New Horizons at equivalent distances due to its gravity assists from both Jupiter and Saturn. In 2012, Voyager 1 crossed the heliopause and entered interstellar space at a distance of about 122 astronomical units from the Sun. It was the first human-made object to leave the Sun's protective bubble. NASA has estimated that if Voyager 1 were heading toward Proxima Centauri, which it is not, the trip would take over 73,000 years. The result is essentially the same. Marginal differences in speed between our fastest spacecraft produce marginal differences in travel time across interstellar distances. Whether the trip takes 73,000 years or 78,000 years is irrelevant. Both numbers represent a duration so far beyond any human framework that they are functionally identical. They both mean never, at least in any sense that a human mission planner could use the word arrive. So let us leave current technology behind. Let us give ourselves a spacecraft 10 times faster than anything we have ever built. Instead of 36,000 miles per hour, imagine a vehicle travelling at 360,000 miles per hour. This is far beyond anything existing propulsion systems can achieve for an interstellar cruise, but it is a useful thought experiment. At 10 times the speed of New Horizons, the journey to Pluto drops from 9.5 years to roughly 14 months. That is a dramatic improvement. A Pluto mission lasting just over a year instead of a decade would transform outer solar system exploration. Multiple missions could be flown within a single scientist's career. The outer planets and the Kuiper Belt would become accessible on timescales comparable to current Mars missions. But at that same speed, the journey to Proxima Centauri would take approximately 7,800 years. You have multiplied the speed by 10, and the interstellar travel time has dropped from 78,000 years to 7,800 years. Still longer than recorded human history. Still longer than the age of the oldest known human settlements. Still a duration that makes the word mission meaningless. You have built a spacecraft 10 times faster than anything humanity has ever produced, and it still cannot reach the nearest star within the lifespan of a civilization. Let us push harder. Much harder. Let us jump to 1% of the speed of light. Light travels at approximately 670 million miles per hour. 1% of that is 6.7 million miles per hour. This is roughly 186 times faster than New Horizons. No chemical rocket, no ion drive, no nuclear thermal engine currently in existence or on any drawing board can sustain this velocity for an interstellar cruise. But let us imagine it anyway. At 1% of the speed of light, the journey to Pluto collapses to approximately 23 days. 3 weeks. You launch from Earth, and before the next month's rent is due, you have arrived at Pluto. The dwarf planet that consumed nearly a decade of New Horizons operational life becomes a casual 3-week trip. At this speed, Pluto stops feeling far away. It starts feeling like a destination you could visit on a long vacation. The entire outer solar system, from Jupiter to the Kuiper Belt, becomes a navigable space. Missions to Neptune and Uranus could be completed in days rather than years. The solar system, at 1% of light speed, becomes small, but at 1% of the speed of light, the journey to Proxima Centauri takes 424 years. You have accelerated to a velocity nearly 200 times faster than any spacecraft ever built. a velocity that would require revolutionary breakthroughs in propulsion technology, and the nearest star still demands a journey lasting more than 4 centuries. Christopher Columbus sailed to the Americas in 1492. 424 years after that is 1916. A spacecraft launched at 1% of light speed during the Age of Exploration would not arrive at Proxima Centauri until the middle of World War I. The passengers, if there were any, would have been dead for dozens of generations. Their descendants, if the ship somehow sustained a breeding population, would have no living memory of Earth. No cultural connection to the civilization that built the vessel. The ship would arrive as an artifact, not a mission. 4 centuries of transit time does not merely challenge human patience. It exceeds the lifespan of most nations, most languages, and most political systems. Notice what is happening. At 1% of light speed, Pluto has become trivially close. 23 days. A commute. And Proxima Centauri remains brutally, punishingly far, 424 years. The speed increase demolished the solar system journey and barely dented the interstellar one. The category gap between these two destinations is not narrowing, it is revealing itself. Let us push to 10% of the speed of light, 67 million miles per hour. This is the realm of speculative physics. No existing or near-term technology can accelerate a crude spacecraft to this velocity. Even the most ambitious theoretical proposals, such as nuclear pulse propulsion or antimatter drives, face extraordinary engineering challenges at this speed. But let us grant it anyway, because the math is what matters here. At 10% of light speed, Pluto is reached in approximately 2.3 days, 55 hours. You launch on Monday morning and arrive at Pluto on Wednesday afternoon. The journey that defined a generation of planetary science, the mission that took 9.5 years and required a gravity assist from the largest planet in the solar system, now fits inside a long weekend. Pluto has become a day trip. At this velocity, you could visit Pluto, collect your data, and be home within a week if you could decelerate and return at the same speed. The entire concept of Pluto as a distant object ceases to exist. It becomes a neighborhood errand, and at 10% of light speed, the journey to Proxima Centauri takes 42.4 years. Let that sink in. You are traveling at 67 million miles per hour. You are moving at a speed so extreme that it could carry you from Earth to Pluto in less time than it takes to binge a television series. And the nearest star still requires 42 years. A person who departed Earth at age 25 would arrive at Proxima Centauri at age 67. Assuming the spacecraft could somehow sustain this speed for the entire journey, they would spend their entire working life in transit. They would depart as a young adult and arrive as a retiree. Their children, if born on board, would grow up having never seen a sky, never breathed unrecycled air, never stood on solid ground. And this is assuming 10% of light speed, a velocity so far beyond current capability that no credible engineering timeline exists for achieving it with a human-carrying vehicle. This is the speed at which the category break becomes emotionally undeniable. At 10% of light speed, the solar system has effectively been conquered. Every planet, every moon, every dwarf planet, an asteroid can be reached in hours or days. The entire gravitational domain of our Sun becomes a compact, accessible neighborhood, and the nearest star still sits 42 years away. You have solved the solar system, and you have not even begun to solve interstellar space. They are different problems. They require different timescales. And the gap between them is not a matter of incremental improvement. It is a wall. Let us go further. 20% of the speed of light, 134 million miles per hour. This is the velocity that the Breakthrough Starshot project proposed for its fleet of tiny laser-propelled nanocrafts, announced in 2016, with $100 million in initial funding from the entrepreneur Yuri Milner and endorsed by the physicist Stephen Hawking. Breakthrough Starshot envisioned a ground-based array of powerful lasers pushing gram-scale spacecraft attached to meter-wide reflective sails, accelerating them to 20% of light speed within minutes of launch. The concept was scientifically sound in principle. Photon pressure on a reflective surface can indeed accelerate a sufficiently light object to relativistic speeds if enough energy is applied. The engineering challenges, however, proved daunting. The laser array would need to deliver roughly 100 gigawatts of power. The sail material would need to survive that energy flux without melting. The nanocrafts would need to carry functional cameras and transmitters weighing only a few grams. And at 20% of light speed, even a collision with a grain of interstellar dust could be catastrophic. As of 2025, the Breakthrough Starshot project was reported to be on indefinite hold. Having spent roughly $4.5 million of its initial budget on about 30 research contracts, no prototype had been launched. No laser array had been built. The vision remained compelling, but the technology remained distant. Researchers at institutions, including the California Institute of Technology, continued working on related light sail experiments, successfully measuring radiation pressure on ultrathin membranes in laboratory settings in 2025. The science is progressing, but the gap between a laboratory demonstration and an interstellar mission remains vast. But let us grant the speed anyway. 20% of light speed. At that velocity, Pluto is reached in approximately 28 hours, 1 day and 4 hours. You launch in the morning, sleep through the night, and wake up at Pluto. The most remote targeted flyby in human history has been reduced to an overnight trip and Proxima Centauri. 21 years. Still 21 years. At a speed so extreme that the entire Pluto mission compresses into a single day, the nearest star still demands more than 2 decades. A child born on launch day would be old enough to legally drink alcohol in most countries before the spacecraft arrived. 21 years is manageable compared to 78,000. Certainly. It fits within a human lifetime. It is the first speed on our list where the word arrive stops sounding like a joke for the interstellar journey. But 21 years is still an enormous commitment. And remember, this assumes a crewless nanocraft the size of a postage stamp, not a crewed vessel. Scaling this technology to carry humans, with life support, radiation shielding, food, water, and living space, would require a spacecraft many orders of magnitude heavier than a gram-scale chip. The energy required to push a crewed vessel to 20% of light speed is not merely larger than what Breakthrough Starshot proposed. It exists in a different universe of engineering. No one has even begun to outline a credible path to that capability. Let us make one final leap. 50% of the speed of light, 335 million miles per hour, half the speed limit of the universe. This velocity is so extreme that relativistic effects begin to matter. Time dilation, mass increase, and the energy requirements dictated by Einstein's special relativity start to impose constraints that no amount of engineering cleverness can circumvent. The energy required to accelerate even a modest mass to 50% of light speed is staggering. For a single kilogram of payload, the relativistic kinetic energy at half light speed is approximately 14 quadrillion joules. That is roughly equivalent to the energy released by 3.3 million tons of TNT, or about 220 times the energy of the atomic bomb dropped on Hiroshima, for a single kilogram. A crewed vessel massing thousands of tons would require energy outputs comparable to the total annual energy consumption of entire civilizations. And this is only part of the energy problem. These numbers describe the kinetic energy of the payload alone. They do not account for the fuel required to generate that energy, and fuel is where the mathematics becomes truly merciless. The Tsiolkovsky rocket equation, the foundational formula governing all rocket propulsion, dictates that the mass of fuel a spacecraft must carry grows exponentially with the desired change in velocity. Double the target speed, and you do not merely double the fuel, you square the fuel ratio, sometimes worse, depending on the efficiency of the engine. For a conventional chemical rocket attempting to reach even 1% of light speed, The required fuel-to-payload ratio is so enormous that the mass of propellant would exceed the mass of the observable universe. That is not an exaggeration. It is a mathematical consequence of the exponential relationship between velocity and fuel mass applied across interstellar scales. Chemical rockets are simply the wrong tool. They cannot do this, not with better engineering, not with larger fuel tanks. The physics forbids it. More advanced propulsion concepts reduce this ratio but do not eliminate it. Nuclear thermal propulsion, which heats hydrogen fuel using a fission reactor, offers roughly twice the exhaust velocity of chemical rockets. Nuclear pulse propulsion, the concept behind the 1950s Project Orion, which would have detonated nuclear bombs behind a spacecraft to push it forward, could theoretically achieve exhaust velocities 10 to 20 times higher than chemical engines. Even fusion propulsion, still entirely theoretical for spacecraft applications, would push exhaust velocities higher still. But none of these technologies escape the fundamental exponential relationship. Every increase in target cruise speed demands a disproportionately larger increase in fuel mass. At 10% of light speed with a fusion drive, a spacecraft carrying 100 tons of payload would need thousands of tons of fuel, possibly tens of thousands. Depending on the specific impulse of the engine and whether the mission includes deceleration at the other end, the mass of the fuel becomes the dominant engineering problem, dwarfing every other consideration. You are not building a spacecraft at that point, you are building a flying fuel tank with a tiny payload attached. This is why the breakthrough Starshot concept was so radical. By reducing the payload to a few grams, it sidestepped the fuel problem entirely. You do not carry fuel on a light sail. The energy comes from an external laser left behind on the ground. The spacecraft accelerates and then coasts forever, carrying no engine and no propellant. But that elegant solution only works for gram-scale chips. The moment you try to scale the concept to carry a human crew, with life support and food and water and shielding, the mass climbs from grams to tons, and the energy required to accelerate that mass to 20% of light speed returns to civilization-scale quantities. The laser array that could push a 4-gram nanocraft would need to be multiplied in power by factors of billions to push a crewed vessel. The energy problem does not go away. It waits, patiently, for any mission ambitious enough to carry something heavier than a postage stamp. But set all of that aside. Grant the speed. Fly at 50% of light speed. At that velocity, Pluto is reached in approximately 11 hours, less than half a day. You could launch before breakfast and arrive before bedtime. Pluto, at half the speed of light, is closer in travel time than a flight from New York to Sydney. The solar system has not just been conquered, it has been trivialized. Every object orbiting the Sun is reachable within a matter of hours. The very concept of distance within the solar system evaporates, and Proxima Centauri takes 8.5 years. You are traveling at 335 million miles per hour. You have compressed the Pluto trip into a morning commute, and the nearest star still requires 8.5 years, nearly as long as the actual New Horizons mission to Pluto took in real life, at a speed nearly 10,000 times slower. The symmetry is brutal. At one of the most extreme velocities physics can meaningfully support for a massive object, the interstellar journey to the nearest star takes roughly the same amount of time that the Pluto journey took using today's technology. You have multiplied speed by a factor of nearly 10,000, and the interstellar travel time still sits in the same general range as a current generation outer solar system mission. The numbers are mocking you. They are telling you that the distance to Proxima Centauri is so absurdly vast that even ludicrous speed increases only bring its travel time down to what we currently consider barely tolerable for a robotic flyby within our own solar system. Let us put all of these numbers side by side, because the pattern they reveal is devastating. At New Horizons speed, roughly 36,000 miles per hour, Pluto takes 9.5 years. Proxima Centauri takes 78,000 years. At 1% of light speed, Pluto takes 23 days. Proxima Centauri takes 424 years. At 10% of light speed, Pluto takes 2.3 days. Proxima Centauri takes 42 years. At 20% of light speed, Pluto takes 28 hours. Proxima Centauri takes 21 years. At 50% of light speed, Pluto takes 11 hours. Proxima Centauri takes 8.5 years. Watch what happens to the Pluto column. It drops like a stone. 9.5 years, 23 days, 2.5 days, 28 hours, 11 hours. Each speed increase crushes the Pluto travel time into something smaller, more manageable, more human. Pluto goes from an extreme decade-long mission to an overnight layover to a half-day hop. The distance to Pluto is large by everyday standards, but small enough that dramatic speed increases can domesticate it. This is what happens when you apply faster technology to a distance that, while enormous in human terms, is still fundamentally a solar system distance. The problem yields. The numbers bend. The destination becomes accessible. Now watch the Proxima Centauri column. 78,000 years, 424 years, 42 years, 21 years, 8.5 years. Yes, it shrinks. Nobody is denying that faster speeds produce shorter travel times, but the rate of shrinkage is completely different. At 1% of light speed, the Pluto trip has already been reduced to a matter of weeks, practically trivial. At that same speed, Proxima Centauri still demands more than 4 centuries. You have to push all the way to 10% of light speed before the interstellar journey even drops below a single human lifetime. And 10% of light speed is not a technology challenge. It is a civilization-scale engineering problem that no one alive today knows how to solve for a meaningful payload. The pattern reveals a mathematical truth that no amount of optimism can overcome. Speed improvements reduce travel time linearly. Double the speed, halve the time. But the distance to Proxima Centauri is not double the distance to Pluto. It is 6,800 times the distance. To compensate for a factor of 6,800 through speed alone, you would need to travel 6,800 times faster than the speed that already felt fast enough for a Pluto mission. New Horizons travelled at 36,000 miles per hour. Multiply by 6,800. You get approximately 245 million miles per hour, or about 36% of the speed of light. That is the speed you would need to reach Proxima Centauri in the same 9.5 years that New Horizons took to reach Pluto. More than a third of the speed of light, sustained for nearly a decade, for a journey to the nearest star, and we have not yet discussed slowing down at the other end. This is the trap. Inside the solar system, distance is a problem that better engines can solve. Build a faster rocket, use a bigger gravity assist, accept a longer coast phase, and you will get there. The timescales remain within human institutional memory. Space agencies can plan missions, fund them, build them, launch them, and receive results within the career spans of the people who conceived them. Pluto pushed that model to its limits, but did not break it. The New Horizons team waited a long time, but they waited within the structures and lifespans of normal human activity. Interstellar distance does not work that way. It is not a larger version of the solar system distance. It is a qualitatively different thing. The speeds required to cross it in human-relevant timeframes do not merely exceed current technology. They exceed it by factors so large that the comparison between current capability and required capability resembles the comparison between a candle and a star. Both produce light, both involve combustion. But no amount of candle improvement will ever produce a star. The gap is not one of degree, it is one of a kind. And even if someone solved the propulsion problem tomorrow, the difficulties would only begin. A spacecraft travelling at 10 or 20% of light speed faces hazards that simply do not exist at the velocities we use within the solar system. A grain of sand weighing 1 milligram encountered at 10% of light speed would release kinetic energy equivalent to several hundred pounds of TNT. The interstellar medium, thin as it is, contains enough hydrogen atoms and dust grains to pose a continuous bombardment hazard at relativistic speeds. shielding against these impacts adds mass. Added mass requires more energy to accelerate. More energy requires a larger power source. A larger power source adds more mass. The cycle feeds on itself, and every potential solution creates a new problem. Navigation becomes a different discipline entirely. Within the solar system, spacecraft can use well-mapped gravitational fields, precisely known planetary positions, and regular communication with mission controllers on Earth. In interstellar space, there are no landmarks, no reference points between the Sun and Proxima Centauri. The spacecraft must navigate autonomously across 25 trillion miles of featureless void, correcting its own course using onboard star trackers and inertial sensors, with no possibility of real-time guidance from Earth. Communication delays of 4 years each way make ground-based mission control a concept that barely applies. Any crisis must be resolved by the spacecraft itself, or it is not resolved at all. And deceleration, the problem everyone forgets, may be the hardest challenge of all. Getting to Proxima Centauri fast is one thing. Stopping when you get there is another entirely. A spacecraft traveling at 20% of light speed that does not decelerate will fly past Proxima Centauri in a matter of hours and continue into the void beyond. To enter orbit, or even to slow down enough for a meaningful encounter, the spacecraft must shed an enormous amount of kinetic energy. This requires either carrying fuel for a deceleration burn, which dramatically increases the mass that must be accelerated in the first place, or using some exotic method like magnetic sail braking against the interstellar medium, a concept that exists only in theoretical papers. Breakthrough Starshot, notably, planned only for a flyby, not a stop. Its nanocrafts would have screamed past Alpha Centauri at 20% of light speed, captured a few hours of data, and continued into deep space forever. Even the most ambitious interstellar concept ever seriously funded did not attempt to solve the problem of arriving. The speed gauntlet teaches a single unforgiving lesson. You cannot close the gap between Pluto and Proxima Centauri by building faster ships, at least not in any way that resembles the incremental progress that characterizes normal engineering. The Pluto problem and the Proxima Centauri problem are not the same problem at different scales. They are different problems entirely. One is a logistics challenge that our species has already solved. The other is a physics and engineering challenge that our species has not yet begun to solve in any practical sense. The two destinations sit on opposite sides of a divide so deep that increasing speed by a factor of 100 collapses one journey to triviality, while leaving the other measured in lifetimes. Every time you make Pluto feel closer, you expose just how far away the stars actually are. Every speed increase that domesticates the solar system reveals the interstellar gulf in sharper and harsher relief. The numbers are not hiding anything. They are telling you plainly and without mercy that the nearest star belongs to a completely different reality of travel, a reality where the rules we learned inside the solar system do not apply, where the comfortable relationship between faster engines and shorter trips breaks down under the sheer, crushing weight of distance measured in light years instead of astronomical units. And the most unsettling part is not the travel times themselves. It is what they imply about the space between here and there. A gulf of empty vacuum so deep it dwarfs every distance our species has ever crossed. No stops, no resupply, no help, no communication faster than a 4-year round trip. A void so vast that even light needs more than 4 years to bridge it. We are not merely far from the stars. We are separated from them by a kind of distance that our species has no experience with, no intuition for, and no proven technology to bridge. That realization, the true weight of what the numbers mean, is where we go next. You have now seen the numbers. You have watched the Pluto journey shrink from 9.5 years to 11 hours as speed increased toward 50% of light speed. You have watched the Proxima Centauri journey resist that same acceleration, stubbornly clinging to durations measured in years and decades, even at velocities that would trivialize any destination in the solar system. You have felt, Perhaps for the first time, the specific texture of interstellar distance, the way it absorbs speed, increases like an ocean absorbs stones. You know, intellectually, that Proxima Centauri is roughly 6,800 times farther than Pluto. You know the travel times. You know the ratios. But knowing the numbers is not the same as understanding what they mean. Numbers are abstractions. They sit on a page or float through a narration, and your brain processes them as data. What the numbers actually describe is something much harder to absorb, something that resists comprehension because the human mind was never designed to comprehend it. This final stretch is about that resistance. It is about why the comparison between Pluto and Proxima Centauri does not merely surprise your intuition but fundamentally breaks it. And it is about what that breakage reveals about our true position in the cosmos. Start with the brain itself. The human mind evolved on the savannas of East Africa over several million years. The selection pressures that shaped our cognition were local and immediate. Our ancestors needed to judge the distance to a watering hole, estimate the time to reach shelter before nightfall, and assess whether a predator across a clearing was close enough to be dangerous. The distances that mattered were measured in footsteps, in days of walking, in the visible range of the horizon. A few dozen miles represented the outer boundary of a typical foraging range. A few hundred miles separated neighbouring populations. The entire cognitive apparatus for spatial reasoning that you carry in your skull right now was built to operate at these scales. Feet, miles, days of travel. That is the hardware. When you hear that Pluto is 3.7 billion miles away, your brain does not actually process that number. It cannot. 3.7 billion is not a quantity that maps onto any experience you have ever had or ever will have. What your brain does instead is file it under the label very far away and move on. It uses the same label for the distance to the Moon, the distance to Mars, the distance to Neptune, and the distance to Pluto, because from the brain's perspective, all of these distances fall into the same category, beyond direct experience. The Moon is 240,000 miles away. Pluto is 3.7 billion miles away. Your brain treats these with approximately the same emotional weight, because both exceed the threshold where evolved spatial reasoning stops functioning. This is why the comparison between Pluto and Proxima Centauri is so important and so destructive to normal thinking. It forces you to distinguish between two distances that your brain desperately wants to file in the same folder. Pluto feels like the edge of everything. Proxima Centauri feels like the next step beyond that edge. Your intuition tells you that they are in the same neighborhood of vastness, that one is merely a larger version of the other, that the gap between them is a matter of degree rather than kind. Every number in this script exists to tell you that your intuition is wrong. The gap between them is not a gap, it is a chasm, a category boundary, a wall so high that the entire solar system fits in its shadow. Consider a thought experiment. Imagine shrinking the sun down to the size of a basketball and placing it on a table in front of you. At this scale, the Earth would be a tiny grain of sand orbiting about 28 yards away. Jupiter, the giant that gave New Horizons its gravity assist, would be a marble roughly 146 yards away. Pluto, the destination that consumed a decade of flight time, would be a speck of dust roughly 2/3 of a mile from the basketball, a short walk. A 10-minute stroll through a neighborhood, and you would have crossed the distance that represents humanity's most ambitious targeted flyby in the outer solar system. Now, at this same scale, where the sun is a basketball and Pluto is a quarter-mile walk, how far away is Proxima Centauri? Roughly 4,300 miles. The distance from New York City to Rome. You have walked a quarter of a mile to reach Pluto, and now you must cross the Atlantic Ocean to reach the nearest star. Not drive across a state, not fly to the next time zone. Cross an ocean, on foot, without rest. The basketball sun and the grain of sand Earth are sitting on a table in Manhattan, and Proxima Centauri is a smaller, dimmer basketball sitting on a table in Italy. Between them lies nothing but empty floor stretching across the entire Atlantic. That image, more than any number, captures the truth. The solar system is a room, a small room by interstellar standards. Everything we have ever visited, everything we have ever photographed, everything we have ever touched with robotic hands or bathed in the light of human attention fits inside that room. The sun, the planets, the Kuiper belt, even the most distant spacecraft we have ever launched, all of it exists within 2/3 of a mile of that basketball. And the nearest neighbouring room, the nearest star, sits 4,000 miles away across featureless emptiness. This is why faster engines are not enough. The problem is not that our ships are too slow. The problem is that the void between stars is too large. It is not merely a bigger version of the space between planets. It is a different phenomenon entirely. The space between planets is filled with context. It is bathed in sunlight. It is threaded with solar wind. It contains asteroids, comets, dust, and magnetic fields. Spacecraft traveling through it can use gravity assists, correct their courses with help from mission control, and communicate with Earth in minutes or hours. It is a navigable space. It has structure. The space between stars has none of these features. It is raw vacuum stretching across trillions of miles. That interstellar vacuum is so sparse that if you gathered every atom between the Sun and Proxima Centauri and compressed it into a solid block, you would have a lump roughly the size of a small asteroid, maybe a few miles across. That is all the substance that exists across 25 trillion miles of distance. The rest is nothing. Not the kind of nothing that space agencies deal with when planning missions to Mars or Jupiter. A deeper nothing, a more complete emptiness than almost any other environment in the observable universe outside of the great cosmic voids between galaxy clusters. Interstellar space is one of the emptiest places that exists, and it is the space we must cross to reach even the nearest star. This emptiness creates problems that no amount of speed can solve. Consider the question of communication. Within the solar system, we maintain contact with spacecraft using the Deep Space Network, a collection of enormous radio antennas positioned around the globe. When New Horizons was at Pluto, signals took 4 hours and 25 minutes each way. That delay was inconvenient but manageable. Mission controllers could send a command, wait 9 hours for the round trip, and confirm that the spacecraft had executed it correctly. They could troubleshoot problems within a single working day. At Proxima Centauri, the one-way communication delay is 4 years and 3 months. A round-trip message takes 8.5 years. If you sent a command to a spacecraft at Proxima Centauri right now, you would not receive confirmation that it had been carried out until approximately 2034. If the spacecraft encountered a problem and radioed home for instructions, the solution you transmitted would not arrive until the mid-2030s. By then, the problem would either have resolved itself or destroyed the mission. Real-time control is not merely impractical, it is a physical impossibility. Any spacecraft that reaches Proxima Centauri must be fully autonomous, capable of making every decision without human input, for years or decades at a stretch. The machine must be its own mission control. Now consider the biological dimension. Assume, for the sake of argument, that some future generation solves the propulsion problem and builds a vessel capable of carrying humans to Proxima Centauri. The speed of that vessel determines whether the crew arrives alive. At 10% of light speed, the journey takes 42 years. At 5%, 84 years. At 1%, 424 years. Even at the most optimistic speed, the crew would spend decades sealed inside a metal container hurtling through interstellar vacuum. They would breathe recycled air. They would eat food grown in onboard hydroponic systems or synthesized from stored materials. They would drink water filtered and refiltered from their own bodily waste. They would live, age, and quite possibly die within the confines of a vessel that could never stop for resupply and could never turn back. The psychological burdens of such a journey are as severe as the physical ones. Studies of long-duration spaceflight, including research from the International Space Station, suggest that isolation, confinement, and separation from Earth produce measurable cognitive and emotional deterioration over periods of months. Imagine scaling those effects to decades. The crew would watch Earth recede into the background of stars until it became indistinguishable from any other faint point of light. They would lose real-time contact with friends and family. They would lose contact with current events. News from Earth would arrive years after it happened, describing a world that had moved on without them. After a decade in transit, the crew would be responding to information about an Earth that no longer existed in the form described. They would become, in a meaningful sense, a civilization unto themselves, disconnected from the species that built their ship. The radiation environment alone poses a threat that has no parallel in solar system exploration. Within the heliosphere, the Sun's magnetic field provides a degree of shielding against the most energetic galactic cosmic rays. Astronauts on the International Space Station orbit within that protective bubble. Even the Apollo astronauts who traveled to the Moon remained inside the heliosphere for the entirety of their missions. A crew traveling to Proxima Centauri would leave that bubble early in the journey and spend years or decades exposed to the full intensity of galactic cosmic radiation. These are not solar flares or coronal mass ejections, events that come and go. These are high-energy particles from distant supernovae and other astrophysical processes streaming through the galaxy in every direction at all times. They penetrate spacecraft hulls, they damage DNA, they increase cancer risk, they degrade cognitive function over long exposures. Shielding against them requires either massive amounts of material, which adds weight that must be accelerated to interstellar cruise speed, or active magnetic shielding systems that do not yet exist at the scale required. The human body was not designed for interstellar space. It was designed for a thin band of atmosphere on a rocky planet 93 million miles from a medium-sized star. Taking it anywhere else is a compromise. Taking it to another star is a gamble measured in lifetimes. And if the journey lasted longer than a single human lifespan, the concept of a crew ceases to apply entirely. At 5% of light speed, the 84-year journey could theoretically be completed within the outer limits of a single very long human life, but only if the crew departed as young adults and survived to extreme old age in a space environment. More realistically, the trip would require what engineers and science fiction writers call a generation ship, a vessel large enough and self-sustaining enough to support multiple generations of humans born, raised, and died in transit. The people who arrived at Proxima Centauri would not be the people who left Earth. They would be the grandchildren, or great-grandchildren, of the original crew. They would have no memory of Earth, no experience of open sky, natural weather, or the feeling of wind on skin. Their entire world would be the ship. And the ship would need to function flawlessly, without external resupply or repair, for the better part of a century. The engineering requirements for a generation ship are so extreme that they border on the absurd. The vessel would need to maintain a breathable atmosphere for decades without leakage, not a slow leak that ground crews can patch during a maintenance window, but zero meaningful atmospheric loss across a span of time longer than most nations have existed in their current form. It would need to sustain agriculture sufficient to feed a stable population, which means soil management, crop rotation, pest control, and nutrient cycling, all within a sealed environment where a single systemic failure in the food chain could mean starvation. It would need medical facilities capable of handling every possible illness and injury without resupply, including surgical capability, pharmaceutical manufacturing, and psychiatric care for a population living under conditions of permanent confinement. It would need genetic diversity sufficient to avoid the problems of inbreeding across multiple generations, which population genetics suggests requires a minimum founding population of several hundred individuals, possibly more. It would need a social structure resilient enough to survive political upheaval, interpersonal conflict, and the existential weight of knowing that the passengers are permanently separated from the rest of humanity. It would need power systems that function reliably for longer than most power plants on Earth have ever operated. And it would need all of this while travelling at a significant fraction of the speed of light, adding the hazards of relativistic dust impacts and navigational precision. across trillions of miles of featureless void. Consider what happens when something goes wrong. On the International Space Station, a malfunctioning system can be repaired using spare parts launched from Earth on a resupply mission within weeks. On a generation ship halfway to Proxima Centauri, there are no resupply missions. Every spare part that will ever be needed must be carried from departure or manufactured on board. Every skill that will ever be required must be taught to successive generations within the ship's own educational system. If a critical system fails and no one on board knows how to fix it, the ship dies. If a disease emerges for which no treatment was packed, the crew suffers without recourse. If a social breakdown occurs, a mutiny, a schism, a collapse of the governance structure that keeps the community functioning, there is no external authority to intervene. The ship is a world, and it must be a world that never fails, because failure in interstellar space is permanent and total. No one has built anything remotely resembling this. No one has designed anything resembling this at a level of engineering detail that would survive a serious review. The concept exists in academic papers and in fiction, and the gap between those domains and actual construction is as vast as the interstellar distances the concept is meant to cross. This is the deepest lesson of the Pluto to Proxima comparison. It is not simply that Proxima Centauri is farther. It is that the nature of the journey changes completely. A mission to Pluto is a feat of engineering and patience, conducted within the support structure of an existing civilization. The spacecraft is built by a space agency with a budget. It is launched from a facility with infrastructure. It is tracked by a network of ground stations. It communicates regularly with human controllers. When it arrives, its data is transmitted back to Earth and analyzed by scientists who were alive when the mission was conceived. The entire enterprise fits within the institutional, biological, and temporal frameworks that humans already possess. A mission to Proxima Centauri fits within none of those frameworks. It exceeds the lifespan of individual humans, the tenure of governments, the funding cycles of space agencies, and the cultural continuity of civilizations. The spacecraft cannot rely on ground support. The mission cannot be guided in real time. The journey cannot be completed by the people who begin it, unless speeds far beyond current capability are achieved. The destination cannot be reached by any existing or near-term propulsion system in any time frame that a living human could experience as arrival. Every familiar structure through which humans organize ambitious projects, careers, institutions, nations, and generations is too small to contain an interstellar mission at current or near-future speeds. And here is the thought that should linger longest. We are not talking about a distant star. We are not talking about some exotic object halfway across the galaxy. We are talking about the nearest star, the first one, the closest possible interstellar destination that the universe offers from our position. If Proxima Centauri were in a different part of the galaxy, its inaccessibility might feel like a consequence of bad luck, an unfortunate placement that puts the nearest star just out of reach. But Proxima Centauri is not unusually far for a star. It is unusually close. The average spacing between stars in the Milky Way's disk is on the order of 5 light-years, and many stars are separated by far greater distances. Proxima Centauri, at 4.24 light-years, is a gift. It is the best-case scenario, and the best-case scenario already exceeds every human framework for travel, communication, and mission planning. This is what the comparison reveals. Not that space is big, which everyone already knew in a vague and comfortable way, but that there is a specific, quantifiable boundary between the kind of distance humans have learned to navigate and the kind of distance that makes human navigation almost meaningless. That boundary falls between the outer solar system and the nearest star. It falls between Pluto and Proxima Centauri. On one side of the boundary, distance is a problem we can solve with better engineering, more patience, and longer timelines. On the other side, distance transforms into something that challenges not just our technology, but our biology, our psychology, our social structures, and our basic understanding of what it means to go somewhere. Pluto took 9.5 years and we celebrated. We had earned that celebration. The New Horizons mission was a genuine triumph. But the celebration carried a hidden assumption that reaching Pluto brought us closer to the stars. It did not. The distance to Proxima Centauri is not shortened by 1 inch when a spacecraft reaches Pluto. The interstellar void does not care about our achievements in the outer solar system. It sits exactly where it has always sat, 25 trillion miles wide, indifferent to every milestone we place on the near side. Pluto is our front porch. We have learned to walk to it. We have learned to stand on it and look outward. And what we see from that porch is not the beginning of an interstellar highway. It is the beginning of an ocean so wide that no vessel we have built, no vessel we can currently design, and no vessel we can build within any time frame a living person would call soon, can cross it. The solar system and the stars are separated not by a distance, but by a category of distance. One belongs to the world of human experience. The other belongs to something else entirely. And yet there is something remarkable in the fact that we know this. We are a species that evolved to track prey across African grasslands, and we have measured the distance to the nearest star with a precision of a few decimal places. We cannot reach Proxima Centauri, but we know exactly how far away it is. We know its mass, its temperature, its spectral class, and the orbital periods of its confirmed planets. We have instruments sensitive enough to detect the gravitational wobble caused by a planet 1/4 the mass of Earth, orbiting a dim red dwarf 4 light-years away. We cannot cross the void, but we can see across it with extraordinary clarity. That clarity is both a gift and a torment. We know what is out there. We know that the nearest star has planets. We know that one of those planets sits in the habitable zone. We can calculate, down to the hour, how long it would take to reach it at any speed we choose. We can design, on paper, the spacecraft that might someday make the journey. We can simulate the trajectories, model the hazards, and estimate the energy budgets. Everything about the problem is understood except how to solve it. We are standing at the edge of the ocean, understanding its chemistry, mapping its currents, calculating its depth, and possessing no boat. Perhaps the most human response to this situation is not frustration but something quieter, something closer to awe. We are a species that has existed for roughly 300,000 years. For most of that time, we did not know that other stars were suns. We did not know that the Milky Way was a galaxy. We did not know that the faint points of light above us were separated by distances measured in trillions of miles. We learned all of this within the last few centuries, an eye blink in evolutionary time. And now we stand at a moment when we can see farther and more clearly than any previous generation, and we are confronted with the honest scale of the problem. The stars are not hiding. They are not receding. They are not playing tricks. They are simply far away, and far away means something different out there than it means in here. The distance between Pluto and Proxima Centauri is not just a number. It is a mirror. It shows us exactly where we stand as a species. We are a civilization that has mastered its local environment with extraordinary precision, that has extended its reach to the outermost objects orbiting its parent star, and that has done so within the natural timescales of human life and human institutions. We are also a civilization that has not yet crossed the threshold from local mastery to interstellar capability. We sit on one side of a divide so vast that it makes our greatest achievements look like practice runs, and the nearest destination on the other side of that divide, the very first step beyond our sun's dominion, already demands capabilities that do not exist and may not exist for centuries. The real shock is not that Proxima Centauri is far away. You already knew that, in the abstract, detached way that people know about large numbers. The real shock is that Pluto, the destination that felt like the edge of everything, is not the edge of anything. It is local. It is nearby. It belongs to the same compact navigable neighborhood as Mars, Jupiter, and Saturn. The entire solar system, from the Sun to the farthest reaches of the Kuiper Belt, is a tiny pocket of accessible space, surrounded on all sides by a void so immense that the word distance barely applies to it. And beyond that void, at the far end of 25 trillion miles of nothing, sits a small, dim red star, the closest one, the first one, the beginning of everything else. It has planets. It has a habitable zone. And it is so far away that reaching it would require a complete reinvention of what human travel means. We reached Pluto in 9.5 years. It took every tool we had, every trick of orbital mechanics, every year of patience our institutions could sustain. And we touched something real. We saw nitrogen glaciers and ice mountains, and a heart-shaped plain on a world 3.7 billion miles from the warmth of our sun. It was one of the great achievements of our species, but the nearest star is 6,800 times farther away. And somewhere in that ratio, between the dwarf planet we celebrated reaching and the red dwarf we can only observe from afar, lies the border between what humans have done and what humans have not yet learned to do. That border is not going away. It is not shrinking. It will sit exactly where it sits today for as long as the stars burn in their current positions, waiting patiently, silently, and with the absolute indifference of the universe, for a species that knows precisely where it needs to go and has not yet figured out how to get there.